learned delegates, and ladies and gentlemen, a very good morning to you all. Sorry for the technical glitch that we had. It gives me immense pleasure to welcome you back to the third and final day of the International Conference on Applied Algorithms, Icaa 2026. After a memorable cultural evening yesterday, we return this morning with a highly intellectual agenda. To set the context for the few hours, allow me to briefly outline the schedule for the first session. We have structured the morning into three distinct segments. First, we'll begin with an invited talk focusing on anytime algorithms and functional dependencies. This will be followed by a technical session from Track B, where we'll witness 5 research presentations delivered in hybrid mode. Finally, we'll conclude the session with a second invited talk exploring Boolean functions and cryptography. To commence these proceedings, we are absolutely honored to have Professor Mandar Mitro as our session chair for the first segment. Professor Mitro is a prominent academic and researcher in the field of computer science, currently serving as professor in the Computer Vision and Pattern Recognition Unit at the Indian Statistical Institute, ISI, Kolkata. He is an alumnus of the Indian Institute of Technology, Kanpur, where he completed his Bachelor of Technology, and then went on to earn his PhD from Cornell University. Professor Mitro's primary research interest lies in information retrieval. He is well regarded for his work on fundamental IR problems. He plays a vital role in the information retrieval community in India and globally. He is a key organizer and contributor to FIRE, Forum for Information Retrieval Evaluation, a major platform that fosters IR research, specifically focusing on Indian language retrieval. Professor Mitro, I now hand over the proceedings to you for the first invited talk by Professor Gautam Das from UT Arlington, USA.
Thank you, Aritra, for the introduction. It's an honor to introduce Professor Gautam Das, first speaker for this morning's session. Professor Das is Associate Dean for Research, College of Engineering at the University of Texas, Arlington. He's also a Distinguished University Chair Professor of Computer Science and Engineering, Director of the Center for Artificial Intelligence and Big Data, and Director of the Database Exploration Laboratory at UT Arlington. It's an honor that he's also an alumnus of the institute I had the privilege of going to. He graduated with a BTech in computer science from IIT Kanpur and has a PhD in computer science from the University of Wisconsin-Madison. He has published over 200 papers, many of which have appeared in premier data mining, database, and algorithms conferences and journals. He has been on the editorial board of ACM Transactions on Database Systems and IEEE Transactions on Knowledge and Data Engineering. He's a fellow of the IEEE as well as a fellow of the ACM. Professor Das, if you're ready, maybe we could start your talk.
Yes, I'm ready. Thank you very much, Dr. Mitra, for the kind introduction, and good morning, everyone. My apologies for not being able to be there in person. I've enjoyed visiting and attending the conference in previous years in person, but this time I could not do it. So I'm having to make this remote presentation. It's about 10 p.m. here on Thursday evening in Dallas, Texas, but I assume it's a good, nice morning for you all out there on Friday. Okay, so without further ado, let me start sharing my screen, which will contain some of my presentation slides. Let me know if this is visible to everybody.
Yes, sir, we can see your slides.
Okay, excellent. Okay, so what I'm going to talk about today is this title, Anytime Algorithms for Approximate Functional Dependencies. And let's see what we mean by that. So what are anytime algorithms? So those of you who are in algorithms research would understand what this means, but perhaps there are others in the audience for whom this may be a somewhat unfamiliar phrase. So let me spend a couple of minutes describing what we mean by anytime algorithms. So in computer science, generally most algorithms are designed to run to completion. They are, they do a fixed amount of computations, a fixed amount of data being read, and then they come up with a single answer. But however, in some cases, users may want to terminate the algorithm prior to completion. So an anytime algorithm is an algorithm that is interruptible. In other words, even before it sort of officially completes, if you stop it, it still has an answer. So it is really answering the question that was put to it, the computation question that was put to it at any time during its computation. And this is a sort of an area of research in algorithms, and there's a lot of examples of that. As a classic example would be, let's say you would compute the traveling salesman route for a bunch of cities. So a typical algorithm will take the bunch of cities as input and it'll run for some time and then it'll produce the best route. But an anytime algorithm would be something slightly different, where let's say it starts up by creating some kind of a route which may not be the most optimal, and then starts making all these local changes to improve it at every point in time, so that eventually when it finally ends, it gets you the right answer. But you can stop it anytime before that, and you still can get an answer. It may not be the best answer, but it still is an answer. So that's what we call anytime algorithms. Now, a subfield of anytime algorithms is anytime algorithms for machine learning and data science, which is really the domain that I have interest in. So here, when we talk about machine learning and data science, the focus shifts from somewhat into the challenges of big data. So data access is typically very costly. And in many cases, the analyst doesn't own the data. The data is owned by a third-party provider. And there is a certain rate limit by which the data is revealed to the analyst. There could be all kinds of privacy constraints on the data. So getting access to the data is a challenge. So if you want to do data analytics, or you want to do machine learning or some kind of model building over this sort of hard to access data sets, what happens is you need to design anytime algorithms, because you really cannot afford the luxury of waiting till the very end until you've gotten access to all the data before you can declare that your model has been built or your analysis is complete. You should be able to give partial analysis ahead of time. So that's the need or the motivation for doing something like this. So in slightly more precise terms, in our case, in the case of ML and data science, we think of anytime algorithms as that which operates progressively over data. And at any point in time, if you interrupt the algorithm, you get a feasible solution. It may not be the optimal solution, but it's a feasible solution. And what we want to also include in our requirements is that we should give a quality guarantee. It shouldn't be just a random heuristic which produces some answer at any point in time. We would like to give some kind of quality guarantee that this is how well we have produced an answer. And the quality guarantee is typically characterized by trying to give very concrete, deterministic upper and lower bounds on the final objective. And again, some of this will become clearer as we go deeper into the talk. And these bounds, upper and lower bounds, will tell you that, okay, you've stopped the algorithm right now. If I were to read the entire data set, I would get a result, whatever the result could be, whatever model it's trying to build. That should be within these bounds, upper and lower bounds that I've calculated thus far. So that's the kind of quality guarantee we want to give here. And the other thing is that as we read more and more data, these bounds tighten monotonically. So these are all requirements. And of course, sometimes it's very difficult to get these requirements because the problem can get very complicated. But this is what would be our sort of expectation when we try to design anytime algorithms. So we're trying to design principled algorithms to do this interruptible phenomenon. And by the way, I cannot see anybody because I'm basically staring at my screen. So if there's any questions or anything like that, somebody has to somehow connect with me. Otherwise, I'll have to go on. There's no way I can see whether anybody is wanting to ask a question. All right. So I've already mentioned some of the benefits of anytime algorithms. Basically, the main benefit is it's cheap. It's cost-aware analytics. You do not have to read the full database or the full streaming data source before you come up with your analysis. And there's a lot of data sources out there where this thing is pretty important because data is hard to get. Okay, I'll skip over some of the slides which I've kind of repeated already. This slide says that this should be the phenomenon that as you read in more and more of the data, your upper and lower bounds that you're trying to achieve with regard to your final output should be getting progressively tighter. So that's an ideal expectation of a good anytime algorithm. And the reason I've been getting into this area is because one of my students, and I'll be talking about her research in a minute, she has been looking at this field of anytime algorithms for ML and data science, and she has been looking at various different aspects of the entire data science pipeline and trying to see whether you can redesign some of those more classical algorithms in the anytime format. So, for example, during data discovery, and if you take classical algorithms like frequent item set mining or approximate function dependencies or building statistical machine learning models like logistic regression or clustering, decision trees, or even doing feature selection. So all these different things that put together into what are called data science pipelines, all of these could benefit from anytime algorithms rather than algorithms that start and end, and there's nothing else happening in between. So this is the sort of the space in which her research is going on. And in this particular talk today, I'll be focusing on the first box on the left-hand side, which is an approximate function dependency. This is some of the early work that she did, and we'll talk about that for the rest of today and the rest of today's lecture. So again, this is all repeats of some of the things I've said. So the main focus of today is really this particular paper, Anytime Algorithms for Approximate Function Dependencies. This was a recent paper. It appeared in the KDD conference this year. The lead author is my student, Sanjeevani Rana. She is one of my PhD students at UTA. And then some of these other co-authors are out here. And I was a part of this team too. All right. Okay, so what are functional dependencies? So those of you who are in the database field would know that very well, but for those who are not, I'll give a very brief description. So imagine that you have a table. You have a table of rows. You have a database table. You have rows which represent tuples, and you have columns representing features, right? So let's say there is a feature X and there is another feature Y. We say that there is a function dependency between feature X to feature Y if for every pair of tuples T1 and T2, if the two tuples agree on feature X, that means they have to agree on feature Y. So this is an example of a function dependency, and it's got a direct relationship with the mathematical definition of the word function. Those of you who are in the database world would realize that functional dependencies have been well studied for the last 30, 40 years because they are very useful in a very classical database issues such as normalization of data sets and so on. More recently, but again, not that recent, somewhat more recently, like 20 years ago or so, the notion of approximate function dependencies also became popular. So the whole idea here is that this dependency may not exactly hold. There may be some violations. So let's say you have a database of 1 million rows. A dependency between X and Y might hold for, let's say, 95% of the table. The remaining 5% may be flawed. So that's an example of what is called approximate function dependency, and this is where some of the data mining research has gone on, and some of the data cleaning research has gone on, because when they try to discover these approximate function dependencies in databases, they are used to flag erroneous tuples and so on and so forth. Now, what we are focused on is taking this classical problem and trying to look at it from any time point of view. So you have got this gigantic database. Now, these classical algorithms to find FDs or AFDs would have to scan the entire database and do a lot of computations to find out which function dependencies, approximate function dependencies exist. But we want to do that in a different way, where we only have some sort of high-level access, high-level information about the data source, but we don't have the full data source in front of us. We are doing get next operations, trying to get a little bit of the data, and then trying to do some estimates of what could be this potential function dependencies or approximate function dependencies. That's really the focus of this paper. Let's take a toy example to make it very concrete. And this, of course, is a very, very toy example. So imagine that you have a database where you have a few tuples. These are possibly, readings of various time and places, certain geographical, climatic conditions. So, for example, the first tuple says that if the season is summer and the humidity was high in that particular place, there was a lot of wind there. The outlook was sunny and the temperature was hot, right? That's an example of a tuple. And the second tuple is, the season is winter and so on and so forth. So you can see that this particular table has 9 rows and it has 5 columns, all right? Now, if we let's focus on the last 2 columns, outlook and temperature. And you can see that in most cases, not all cases, in most cases, if the outlook is sunny, then the temperature is hot. If the outlook is overcast, then the temperature is cool. Now, this is, I said in most cases, because there are 3 tuples, the ones which are colored in orange, where they actually violate, right? There is an example of a tuple where when the outlook is overcast, the temperature is hot. And when the outlook is sunny, the temperature is cool, and so on and so forth, right? So these are some of the violations. Now, if these violations did not exist, then that would be a very nice function dependency from outlook to temperature. So, so there are all these algorithms which try to find function dependencies. Of course, I've described function dependency in terms of one feature implying another feature, but you could go into subsets, right? You could look at the power set of all the features, and you could come up with function dependencies. There might be existing function dependencies between subsets of features implying subsets of features. So this really is a lattice search problem in subsets. And the approximate function dependencies really will need to depend on what kind of erroneous tuples you want to allow in the definitions. So in this particular example, you can see that if we take the two features that I talked about, X being outlook and Z being temperature, you can see that the domain size, that means the metadata associated with X, which is the number of different distinct values of X, unique values, it's only 2, right? It's either sunny or overcast. And likewise, temperature, if I look at temperature, at least in this example, it's only 2, right? Hot and cool. So if you think of a cross tabulation of this data set, right? So that the matrix on the left-hand side, bottom left, tries to just describe that. So if you have rows representing outlook and columns representing temperature in this particular cross-tab matrix, you can think of every cell in this matrix representing the number of correlated pairs. So the first left cell, by the way, tell me if you can see me pointing with my cursor. Is there something you can see? I guess not, because I'm not hearing anybody say yes or no. So I'll have to describe which part of the screen I'm at. So, so this basically, this particular table essentially summarizes the correlations that occur in this particular data set. So if you look at the first column at the bottom, it gives you the marginal information about temperature. So out of this entire table of 9 rows, how many rows has the value of hot for temperature? And the answer is 6. And if you look at the sort of the second column for temperature, for the value cool, you can see that the entire table has 3 rows which have the value temperature is equal to cool. Likewise, horizontally, if you look at this this table, it says that there are 5 rows, 5 tuples which have sunny outlook, and 4 tuples which have overcast outlook. And therefore, the total number of rows add up to total number of tuples add up to 9. Now, the question marks are put here. Question marks are put here is also easily determinable. If you scan the entire database, it tells you how many rows have both outlook equal to sunny and temperature equal to hot, outlook equal to sunny and temperature equal to cool, outlook equal to overcast and temperature equal to hot, and so on and so forth. So these will tell you all the correlations, the number of co-occurrences of each pair. Okay. Now, if you have full access to the database, all of these are easy to compute. And in fact, that's what all these classical algorithms for AFDs and FDs and all do. They fill up this matrix by just doing a full scan of the data set. And once they have this matrix of co-occurrence frequencies, then all this FDs and AFDs and all can be easily, well, not easily, but they can be calculated using very standard methods. What we have as a challenge is that if we haven't read the data, we don't know what these question marks are. Now, we have some broader marginal information at a high level. I mean, before we start reading the data from the data provider may have revealed the fact that there are 6 rows which have temperature equal to hot, or there are 4 tuples which have outlook equal to overcast. And that's typically the kind of statistical information that database owners and database providers provide, but they do not give more fine-grained co-occurrence frequencies. So somehow, as we're designing this anytime algorithm, and as we're reading the data and haven't read a significant portion of the data, we have to start making estimates about what this question marks might be. So that's really, in a nutshell, the challenge in front of us. Okay, so I've already alluded to what might be the error measure. Now, these are very formal definitions of error measures, which have been used in traditional approximate functional dependency literature. In particular, we're going to focus on the last one, which is the G3 error. It simply says that if we have a table and you are looking at a pair of attributes X, and we're trying to determine whether X functionally depends, X functionally decides Y, the error of the functional dependency, and that's why it's called an approximate functional dependency, is the minimum number of tuples that you have to delete from the database so that you can create a complete functional dependency. So again, going back to our toy example, if I got rid of the yellow tuples, the orange tuples in this case, out of 9 tuples, if I got rid of 3 of those, then I'll establish a functional dependency. So the G3 error of the AFD outlook implying temperature in this case is equal to 3 out of 9, right? So our objective in designing functional dependencies and approximate functional dependencies is to try and find out, which particular, either X implying Y or subsets of features implying another subset of features have small errors. So that's really the data mining problem that people have been looking at. So I've already mentioned some of the applications. The functional dependencies, the 100% accurate functional dependencies have lots of classical applications in databases: query optimization, integrity enforcement, database normalization, schema design, so on and so forth. And more recently, somewhat more recently, approximate functional dependencies is used for feature learning, approximate query processing, data cleaning, and all that. And there's a lot of research out there for these problems. So I'm going to move a little faster because some of this stuff I've already kind of alluded to in my previous, mentions by today. You already know that we are talking about trying to find AFDs as we read the data without having read the full data. And we are going to be focused on two kinds of algorithms. One is exact algorithms, where we want to give a precision of 100%, which means that our upper and lower bounds that we give are going to be deterministic, and everything has got to lie within those. And in approximate algorithms, we will also allow for the possibility of false positives and somewhat higher recall earlier. So this is sort of the goal. Again, this slide I can perhaps skip. It simply says that there are a lot of practical areas, applications, where data is hard and expensive to get. What you get is individual attribute distributions or metadata information, but you do not have access to the entire data set. And accessing the data set has a cost associated with it, either time cost or actual monetary cost. A good example of this is what are called deep web databases. So all of us have purchased tickets, airline tickets from online agencies. So for example, when I buy airline tickets of travel within India, I typically use Make My Trip. When I buy, internationally, when I'm in the US, I use Expedia. We also do online purchasing from places like Amazon and all that. Basically, what's happening is that all these are what are called hidden databases. There are gigantic databases sitting behind these web forms, and we don't have full access to these databases. We only have access to these databases in a controlled manner by asking queries, and we get a certain amount of the tuples returned to us. So this is an example of a place where if you want to do real data mining of these big, gigantic databases, it's going to be really difficult because you won't be able to retrieve all the data sets ahead of you because it's going to cost a lot of money. So you can only try to get a few based on how the data provider provides you the data. And then based on that, you have to make all this analytics decisions. So this is an example of, again, a place where anytime algorithms for decision making and functional dependencies and all that are going to be useful. So coming back to the technical side of the discussion, you can see that the core technical challenge is as follows. You have read a certain amount of the data. Like, let's say I have read 5 tuples of those 9 tuples. So if I look at my crosstab matrix, the row constraints and the column constraints are already known to me beforehand. I know that the total number of tuples that have the value hot is 6. The total number of tuples that have the value cool have 3, and so on and so forth. But the co-occurrence numbers we don't have yet. We only read 5. We haven't read all 9. And we have the co-occurrence information for those 5 that we have read. So hot and sunny, there are 2 of them. If you look at that table on the left-hand side, you can see that there are 2 tuples that are hot and sunny. Over hot and overcast, there is only 1. Cool and sunny, there are no tuples yet. And cool and overcast, there are 2. So the question marks have been partially filled up. You remember a few slides ago, I said that there are those question marks that we need to figure out. So they have been partially filled up, but we haven't filled up the whole thing because we haven't read the entire data set. So really the technical problem is as follows. How do I fill up these central cells such that they respect the marginals, the rows and the column constraints? Now, there are, of course, many different ways of filling it up. This is a highly under constrained problem. There are many, many different ways of filling up these 4 cells so that all the red numbers line up. So the question is, which is the right way? And what we're going to do in this work is we're going to show you that there is, we can fill it up in a way in which we get the maximum possible error for the functional dependency that we're trying to estimate, or we can fill it up in a way where we get the minimum possible error. In other words, we can assume the best case of ways in which the values are going to be paired up in the unseen tuples so that we really make the functional dependency as strong as possible. We also can play devil's advocate and try to pair up the remaining tuples that we've not seen in the worst possible way so that the functional dependency is as weak as possible. So that's really the technical challenge in front of us. How do we find out this upper bounds and lower bounds of the G3 error of the functional dependency that we're trying to calculate by filling up this matrix in a way such that the marginal constraints are satisfied, but we get the best possible error versus the worst possible error. So that's really the technical problem. Taking a step back, so far, I've been sort of drawing you to a specific example of a functional dependency. I'm focused on a particular, feature like outlook and another feature like temperature. But as I've told you earlier, in the data mining literature, we're not given a particular pair of features. We're supposed to find out over the power set of all the features which subsets of features functionally define another subset of features. So those of you who are familiar with some of these, power set lattice algorithms that are typically used in some of this data mining problems. So for example, frequent item set mining is a classical example where they use lattices. So that's the kind of technique we're going to use. So nobody's going to give us a pair of features and tell us to find out the approximate functional dependency between this pair of features in an anytime algorithm. They're going to tell us, this is my table. I've only read some part, I haven't read the rest, and I'm giving you some of the high-level statistical marginal constraint information about some of the features. You're supposed to find out which, over the power set of all the features, which subsets of features functionally define other subsets of features. So that's why we got to work with this more general problem. And two sort of specific problems crystallize out of this. One is, since there are many, many different kinds of, there are 2 to the power m different kinds of different instances of potential approximate functional dependency, since each of them will have a different error, a different G3 error, the challenge is find out the one which have the smallest errors. So that's the top K problem. So of all the functional dependencies that have approximate errors, so all the approximate functional dependencies, find out the ones which have the smallest errors. And the second problem is sort of the inverse problem, where an error is defined, like I want only 5% of the tuples to be erroneous, the rest should be, allowed. So given this error tolerance of 5%, find out all the minimal functional dependencies whose G3 error is less than 5%. Now the word minimal simply means here that you cannot make the dependency even linear, that you cannot drop a feature from the left-hand side or a feature from the right-hand side. So that's the minimality requirement here. Now, both these problems have been looked at in the classical literature. There are non-anytime algorithms designed for these. So TANE and Pyro, these are the two sort of well-known ones. All of them require, sucking in the entire data set and doing a lot of lattice exploration. And those are the kind of the baseline algorithms, if you will. What we have done in this work is really looked at it from an anytime angle. Okay, so the main idea behind our work is, one of the main ideas, several ideas are there. One of the main ideas behind our work is, as I mentioned earlier, if you can establish upper and lower bounds, for certain candidate functional dependencies as we're reading the data, then we can use that to do a lot of pruning. You can decide that. So when I'm comparing two particular functional dependencies, potential functional dependencies, I can, and if I've got upper and low bounds for the potential error for these functional dependencies, I can prune one away if its lower bound of its error is larger than the upper bound of the error of the other one. So that's the kind of reason why we can perhaps apply some anytime algorithms to these problems. So here is a good example. I hope this will make some sense. So typically a power set lattice algorithm tries to create, subsets of tuples, sorry, not tuples, subsets of features as potential left-hand sides of functional dependencies. Let's say for simplicity, we only have one feature, which is this feature Z, which is in our case, let's say temperature. So we're trying to figure out which subsets of attributes functionally define temperature, all right? So we can start from the bottom of the lattice, look at all the singleton features. Season, does season imply temperature? Does outlook imply temperature? Does humidity imply temperature? Now, if you had the full data in front of you, you could find out, right? You could just find out the strength of that functional dependency, but we don't have the full data in front of us. However, if we have read partial data and we had some way of computing upper bounds and lower bounds, like let's say you could find the upper bound of season implies temperature, and the lower bound of season implies temperature. That means what is the upper bound and lower bound of the error? Then that can help us with some pruning, right? So for example, if you find that the upper bound of the candidate function dependency season implies temperature, it's smaller than the, let's say the threshold epsilon, it's going to be retained. Whereas if its lower bound is bigger than the threshold epsilon, it's going to be thrown out. So those are the kind of things we can do. And upper bound or lower bound should be easier to calculate after having read partial amount of data than the exact error. So that's the reason why upper bound and lower bound can be a very, very strong tool to help us with our anytime algorithm. So really that is the if you go a little bit deeper, that is the technical challenge in front of us. You have read the data set to some amount, like 10%, 20% of the data. And by the way, here we have to assume adversarial data providers. I mean, there is no particular reason to assume that the data is going to come to you in a particular way. So for example, you cannot use a classical machine learning approach, which is that whatever data patterns you've read so far, you expect that to be what you're going to see in the future. It could be completely adversarial, right? I mean, the data provider may choose to send data to you in a particular manner. That's why these deterministic upper and lower bounds with guarantees are kind of important. So we need to estimate upper and lower bounds. So let's see how we do that. This particular slide is not very informative, or rather it sort of repeats some of the old information, so I'll just move on. Let me try to illustrate this upper bound and lower bound calculations with another example. All right, so we've been talking about temperature, wind, and all of that. Now let's look at a somewhat more whimsical example. So imagine that we have got a sort of set of employees in a corporation, or let's say the students and faculty in a university. And you've got really two features. One is the length of the hair, and the other one is the gender, right? So this is obviously a whimsical example, and we would expect that there is a reasonably good functional dependency between hair length and gender. Like, most of the time, if the hair is long, you expect that gender to be female, whereas most of the time, if the hair is short, you expect that gender to be a male. However, there are, of course, violations of this. So in this particular example of 9 records, there are a few which do not have this, right? So there are, females who have short hair, and there are a few males who have long hair. So this is a good example of a data set where the functional dependency between hair length to gender is pretty good, but not 100%. And what we're going to do is we're going to look at this problem and say that if you have read a few records and not read the rest, what can we say about the upper bound and lower bound? We know that for this particular example, if you could read the entire data set, you know that the violations are going to be, let's see, the violations are going to be E5, E6, and E9. So there are 3 violations. So if you read the full data, a classical approximate functional dependency algorithm would say that the G3 error of this data set is 3 out of 9, right? But if we haven't read the full data set, let's see what we can do. So let's say we have read, so if we had read the full data set, this is what we get. And you can see that the 2 orange cells define the error, that they are the violations. So there are two females who have short hair, and there is one male who has long hair. And if those three were removed, then you would have a perfect functional dependency, and then the error is therefore 3 out of 9, right? But this we don't have this in front of us. What we instead have is we only have read 5 rows out of these 9 rows. So let's say these are the 5 rows we have read, all right? And then we go to our calculations. So now if I look at the left-hand side cross tab, we have read 5 rows. We have read 5 rows out of which there are 2 females with long hair and 2 males with short hair and 1 female with short hair, right? And 0 males with long hair. We haven't read the whole thing. We have only read some part. And thus far, of the 5 we have read, out of those 5, there's a violation of 1 record, right? If you add up the orange or yellow, however that is displayed to you, that'll be 1. So now the question is, you've got still 4 more records, and you've got 4 more records, and you need to fill up these co-occurrence cells with these 4 numbers, such that the margins are respected. But we try to, in one case, when you're trying to calculate the lower bound, we try to minimize the error. That means we try to create favorable pairings so that the error is minimized. And if you want to calculate the upper bound, you try to maximize the error. We try to create the most unfavorable pairings. And you can see that this particular problem, the 2 examples are out there. You can pretend that the stuff that you have not seen ahead of you has pairings so that there is no more error, whereas the upper bound error could become all the way to 3, which is what the real error is. So how do we get this lower and upper bound is really the question. Now with this toy problem, you can actually eyeball it and you can actually calculate it, but these problems can be put into a computational setting, which is what we did in this paper. So I'll not get into the details of some of the theory behind all this, but it's a computationally hard problem. The lower bound problem is an NP-hard problem, and it's got a easy reduction from the subset sum problem. Fortunately, that also gives us, because the subset sum problem is weakly NP-hard, it gives us a lot of opportunities to use fairly strong polynomial time approximation schemes to solve this problem. And then overall, for the overall problem, even for finding upper bounds, we use a variety of algorithmic techniques, which I'll let you read the paper rather than get into it here. The whole problem can be cast as a mixed integer linear program, which of course can be computationally very challenging. And some of the other error forms, like the G2 error and all, they need to be cast as a quadratic program. But then, what we did is we also used heuristics. So for example, we use heuristics like iterative proportional fitting and other greedy heuristics to solve this problem in a more practical manner. So I will skip some of those details, and just as a set of summary of results, the algorithmic side of things, this is a category of algorithms we designed for the upper bound and for the lower bound. We used a relaxed version of the MILP problem was relaxed into a linear program, and we did some rounding to come up with a fast algorithm for the upper bound. Then we used greedy heuristics and also iterative proportional fitting for calculating some of the other error problems. Again, a lot of these details you should read up in the paper if you're interested, or send me email. I can connect you to more information. Let me now go to briefly about the experiments. I don't want to spend a lot of time on the experiments. My objective was to sort of introduce this area of research to folks here as to see what they think about it. But one of the challenges about these experiments or evaluation was, how do we create this data sources, this data ownership, where the data is revealed to you in an adversarial manner. So it's unlike a typical data mining evaluation, you would take a real data set and you would work with it. Here, it's not just a matter of finding a real data set. It's also a matter of deciding how that data is going to be revealed to you, right? So for that, we applied a couple of techniques. One is we made the assumption that a lot of real-world data sets, they are sitting inside large databases, and large databases typically what they have is they have what are called clustered indexes. In other words, they have keys, and the keys could be either a single feature or a pair of features or even a composite of features. And the data is typically sorted according to a primary key. And we assume that the data is going to be sorted in a primary key, and then the data provider is going to return to you data in order of primary key. So that's one of the methods we use to create this, this get next feature. Because doing random shuffling of the data doesn't make a lot of sense, because if you do random shuffling of the data, then even a tiny amount of initial data read will be enough to preserve the patterns of the overall data set. And we are trying to say that that is not the way in which data providers reveal data. They reveal data due to variety of reasons, right? They want to preserve their competitive advantage, or the data may be simply physically stored according to a clustered index. So those are some of the things that we have to worry about. And again, not particularly illustrative to get into some of the details of the experimental results, but let me go to by the way, these slides, I have to thank my student Sanjeevni for putting together, so you would understand these a lot more than I do. But let's go to the summary of these experiments or evaluations. So we had basically two kinds of algorithms. One was those very precise algorithms that used those techniques to calculate upper bounds and lower bounds and gave guarantees that the error of the eventual candidate approximate function dependency, its error has to be within this upper and lower bound. So those were very nice monotonic results, in the sense that as you read more and more data, the upper and lower bound started getting tighter and tighter. So those were the ones which had 100% precision. We also had another kind of algorithms where we use approximations. So in the approximations, we had two models of approximations. One was that instead of let's do informed prior approximations, and then the other one was uninformed prior approximations. So informed prior would mean that, and this is a big assumption, right? Informed prior says that whatever data pattern you've seen so far, you expect a similar data pattern to exist in the future. So if you have seen so far that out of the 5 tuples that you have read, that male and long hair is 40%, male and short hair is 40%, female and long hair is another 40%, and the rest are 20%, you would expect something very similar to happen down the road. So this is making a huge assumption on how the data provider is going to release the data. So with this assumption, we use iterative proportional fitting as an algorithm to fill up the rest of the unknowns using this assumption, staying as close as possible to the initial distribution that you have read. So that, of course, was a strong assumption, and it failed badly when we had data providers where they were sending data in an unpredictable or adversarial manner. The other approximation algorithm we did was what we call the uninformed prior. So the uninformed prior simply says that the future data pairings of the data tuples that you're going to get have nothing to do with what you've read so far, but we'll assume that they're uniformly drawn from a distribution. So it's basically uninformed prior. It's uniformly drawn from a distribution, so that the only thing we ask the distribution to obey is that the eventual constraints or marginal constraints have to be respected. So those were the two approximation algorithms that we used, and we had all kinds of results. using those. Again, a lot of details about some of these results, which I don't want to get into here. But the conclusion is that this particular work is, to the best of our knowledge, is the first one that proposes an anytime framework for doing basically machine learning or data science, where the data is revealed to you in an adversarial manner or in an unpredictable manner. It doesn't have to be adversarial, but at least you cannot make some distribution of assumption on how the data is going to be given to you. So there's a cost associated with data coming in. And this particular piece of work looked at approximate function dependencies, which is one of these well-studied constructs in databases and data mining community with lots of applications. And we took a pretty hard look at this problem and tried to do what we call principled algorithms, principled approaches with guaranteed bounds, and so on and so forth. We also looked at real-world approximate algorithms where we relaxed some of the stringent requirements of being as principled as possible. So, for example, the uninformed prior and the informed prior approaches. And those, of course, worked, they were computationally much faster, and they worked well when the data was actually revealed in the manner in which they were designed to be. So it all depends as to how they work in real world and applications. So as future work, and in fact, I would say ongoing work, because Sanjeev is already looking at applying this anytime model to other machine learning and data mining problems. So for example, so looking at linear regression, classical item set mining, and neural models. So that's really what he's trying to do right now. Okay, so with this, I'm going to stop. I think we're at the end of the hour. I'm going to stop at this point, and if anybody has any questions, I'd be happy to take those.
Dash?
I would like to request Professor Mandar Mitra to please take his seat on the dais. If our audience has some questions for Professor Gautam Das, we'll be happy to take them. So please, you can take your seat and we'll wrap up quickly. If the audience has any questions, we have the runner mic. Anyone has any questions, please, for Professor Das? Sir, any questions? Yes, we have some questions. Sir, they'll give you the mic. I just request you to wait for a while. We'll patch the audio. Bhandari, sir.
Hello.
Just wait. We'll patch the audio. একটুখানি দাঁড়াবেন. We'll patch the audio. Otherwise, he'll not be able to hear you.
Okay. Then Professor Das, it was really nice and I enjoyed this. Frankly speaking, looks like that a lot of uncertainties are coming in, right? In the queries and all those stuff. But I'm wondering that, do you think that in that future work, right, you have mentioned that recommendation system, that part, there, don't you think that support, confidence, all those things, whatever we studied or we use, those things will go off now. We can use directly these things, right?
I'm trying to understand your question a little bit more carefully. So you're trying to say that what we've learned about support and confidence. So let's say association mining, right?
Approximate that FDs, right? So
Yes.
whatever information we can get from that confusion matrix you have designed.
Yes.
So that can be used directly in finding the item sets. That's what
I think so. I think the item set mining problem would probably be the easiest one to solve given this particular framework. Because at the end of the day, if you take this data set and you simply do a one-hot encoding of this data set, where we create Boolean attributes out of each distinct value, then the problem of this problem reduces to item set mining, right? So I think the item set mining problem would be the first one that should be, directly solvable using these techniques. What Sanjeevani is looking at right now is sort of the other problems such as linear regression, logistic regression, those kinds of problems where there is no one-to-one mapping or there's no close mapping from the function dependency problem and those problems. So they require different techniques. But I think what you're saying about item set mining, I would say that that could become a corollary of this work because it's so similar. I don't know if that helps answer the question.
Thank you, sir, so much. I would request Professor Mitro to conclude the talk with his thoughts and thanking our speaker.
Okay, I really had a very peripheral question to ask. You mentioned one of the evaluation, I mean, like the precision and recall, I understand. You also mentioned NDCG at one point of time. So I'm wondering how, I mean, on what basis you do the equivalent of kind of different grades assigned to different approximate functional dependencies?
No, so the NDCG is basically the reason that was used is one of the problems we're trying to do was we're trying to find out the top K function dependencies, approximate function dependencies with the smallest error, right? So that becomes a ranking problem. So for the ranking problem, there is a correct answer, and then there is an approximate answer. And the ways to measure those really is where this NDCG is being used. Because remember that we are not looking at a specific.
So the approximation is what would contribute to a particular item's gain value? Is that how it works?
Okay, let me make it a little more sort of precise, right? Like let's say you have got 10 features, okay? X1 through X10, and then there's another feature Z, which is not what you're concerned about. So then there are 2 to the power 10 different potential function dependencies, right? Because any subset of attributes can be on the left-hand side of a potential function dependency. So there are 2 to the power 10 different function dependencies, and each of them have a particular error, right? Because some of them fit the data very well, some of them don't fit the data very well. And let's say the problem was to find the top K out of this 2 to the power 10 function dependency. Let's say you want to find the top 30 of them, right? So and then if you read the full data, then you of course would get the correct top 30. But when you've read only part of the data, you're going to make some estimates about the rest. So you're going to come up with a set of 30, which may be a little bit different, right? Now, so for this, you can measure precision and recall. And NDCG is used in a weighted manner to measure the rank differences. So again, the details are probably there in the paper somewhere, but it's really used to measure the rank differences. So if you make error close to the 30th level, it's less impactful than if you make errors at the higher levels.
Okay, I think I have an approximate idea of how NDCG works in your setting. But
Okay.
thank you very much for the talk. I mean, certainly as far as I'm concerned, I mean, it opened up a completely new area of research to me, and very interesting talk. We'll thank the speaker and conclude the session then and move on to the break. Thank you very much, Professor Dash.
Thank you. Thank you. Absolutely. Thank you.
In person in further iterations of the.
Okay.
Thank you, sirs, for your valuable, insightful questions and a thought-stimulating discussion. May I now respectfully request Professor Prosenjit Gupta onto the dais? He's been my teacher and guide. To felicitate Professor Mitro. So please, we have a small token of gratitude for you. Auttoryo and some mementos. Please, sir, could you please come forward? Thank you, sirs. Professor Das, thank you so much for your talk. We might be disconnecting now.
Thank you very much. Thank you very much for the opportunity to.
All right, so we'll now take a small short tea break, but we have a very tight schedule ahead of us. So I would request all of you to gather back in 10 minutes by 10:50, please.